right, so welcome to the first session now after the break. My name is Ben Stock from CISPA. I will be your session chair for the next 3 talks. After that, Alfred will take over seamlessly. So please do not run out for the coffee break after the session, because there is no coffee break after the session. This will be called Internet of Everything. It's actually mostly Internet of Things. We have 3 exciting talks in this session. The first one is going to be given by, your slides already on, Yu Qiao. He's a master student from Wuhan University and will tell us how we get from hardware fingerprinting to access tokens. And the audience.
Okay. Hello, everyone. I'm Yu Qiao from Wuhan University. I'm very delighted to share our work with you here. The title is From Hardware Fingerprint to Access Token, Enhancing the Authentication on IoT Devices. This work is a collaboration of Wuhan University, Tsinghua University, Zhejiang University of Technology, and George Mason University. As we know, embedded devices are almost everywhere in our daily lives, such as your car key, your hardware wallet, and the smart homes. In these scenarios, we should provide a reliable authentication for these devices. For example, your car key issues the command is from your car key, but not others. One approach is the token-based authentication. For example, use the secret key to sign the message, but this approach suffers from the token compromise. For example, an attacker may use a flipper 0, a very small device, to copy your car key, such as learning the routing code or just copying the firmware to steal the token. Then the attacker can use the flipper 0 to unlock the car. What we need is an unclonable factor for authentication. But which things is unclonable? We turn to the hardware fingerprints, as the hardware is unclonable. There are 2 ways to use hardware fingerprints for authentication. The first way is use as a new identifier. For example, I combine the original token and the hardware fingerprints together for an authentication. The second way is based on the protocol response. The second way is based on the challenge response protocol. The server gives the challenge, and the hardware gives the response. But there are 2 limitations. The first one, they may need extra hardware. And more importantly, these approaches are still difficult to prevent the man-in-the-middle adversaries. What is the man-in-the-middle adversary? In a word, we should consider insecure communication channel, which means the attacker may listen the channel, tamper your request, and so on. Based on the insecure communication channel, the attacker can launch 2 types of attack. The first one is the reuse attack, which means the attacker can tamper and forward the request from the victims. And the second type is the mimic attack, which means the attacker can use a machine learning model or deep learning model to learn the relationship between the challenge and the response. Then the attacker can give the response to the corresponding challenge. We summarize our threat model here. The attacker is going to attempt to impersonate legitimate devices, and we focus on 3 attacks. The first one is a tampering attack, which means the attacker can tamper and forward the request. The second one is a hardware mimic attack, which means the attacker can use a hardware to mimic the behavior of the legitimate users. And the third one is a software mimic attack, which means the attacker can use a software such as machine learning model or deep learning model to mimic the behavior of the legitimate users. What we want to do is provide reliable authentication for embedded devices, and at the same time, we should resist these 3 attacks. Our solution is a unique hardware-based access token. The key idea of our solution is bind each request to a unique hardware access token. For example, if you unlock your car 10 times a day, we should generate 10 different tokens. There are 3 steps in total. In the first step, we will collect hardware fingerprints in a secure environment for setup. And then we generate the token for the request. And at last, the backend will verify fingerprints. We will use a running example to explain the details of step 2 and step 3. Here, there is a car key want to unlock the car. The original request is as below. There is only one operation, door unlock, in this request. And then there are 3 steps to generate a token. At first, we add announce here. We add announce to the request and use a message mapping here to map the operation and the announce into some predefined hardware tasks. Secondly, the hardware module will execute these predefined hardware tasks to give the results here. We call these results raw fingerprints. And at last, the hardware will partly modify the fingerprints via a method called data poisoning, and then generate the token. The request with the token will send to the backend, and the backend will verify the fingerprints in 3 steps too. The first step is a message mapping tool. Here, the message mapping in the backend is the same with that on the device. So they will get the same hardware task. And then the backend will use a pre-trained fingerprint predictor to give a predicted fingerprints. At last, the backend will use the verifier to compare these 2 fingerprints, to compare the fingerprints from the device and the predicted fingerprints, and then give the final decision, pass or not. This is a whole processing, and then we will use 4 questions to explain the important details and show how we resist these 3 different attacks. The first question is how we select and use hardware features. In a word, we represent a hardware model as arguments fingerprint pairs. We design some hardware tasks for the hardware model. In this way, the hardware will take the arguments as input and output a fingerprint. Then the hardware can be represented as arguments fingerprint pairs. In this way, we also can prevent the hardware mimic attack, as the hardware features are unique among devices with the same arguments. The fingerprints are different among different devices. This picture shows the distribution of among different devices. And the second question is how to ensure the uniqueness of each token. In a word, we will bind tasks to the request via hash function. To make sure the uniqueness, we will add announce to the original request. So even the request have the same operation, they will have different hardware tasks and eventually have different tokens. To resist tampering attack, the hash function will help us because the change to the message will change the task and finally change the token. The third question is how to prevent the software mimic attack. Software mimic attack means the attacker can collect lots of arguments, fingerprint pairs, and learn the relationship between them. One solution is we may design more complex, more difficult tasks, but it is unreasonable because nowadays the deep learning models are so powerful to learn the relationship. So we turn to disrupt the learning process of the attacker. We borrow the idea from the data poisoning, and we partly modify the raw fingerprints. Then the poisoned fingerprints will disrupt the learning process of the attacker. The last question is how to verify token at the backend. In a word, the backend will learn from the hardware and compare fingerprints. For setup, the backend will collect enough arguments, fingerprint pairs, for training the predictor and the verifier. And when it comes to the authentication, we will use multiple fingerprints. And the backend just counts the number of fingerprints that are verified. At last, according to a threshold, the backend will give the final decision. This authentication is passed or not. Yeah. About our evaluation, we implement our design on 3 types of devices, in total 60. And we select 5 different models and 6 different hardware features for authentication. The first evaluation is about the usability of our design for authentication. The results are shown in the left table. When we use multiple fingerprints, this line, the last but one, we will achieve a high true positive with a very low false positive. And about our design to resist various attacks, the results are shown as below. About the template attack, the success rate is less than 0.1%, and for the hardware mimic attack, the success rate is less than 10%. And about the software mimic attack, the success rate, this one is less than 2%. These results show that we can resist these 3 attacks very well. Yeah. Also, we have other evaluations, including the overhead and other problems. If you are interested in it, you may refer to our paper for more details or just raise your questions. Yeah. As a conclusion, we perform a systematic study on hardware features for fingerprinting the MCU devices, and we introduce our design MCU token, a hardware fingerprint-based authentication framework, and we prototype MCU token and demonstrate its usability and performance to resist different attacks. Yeah. That's all. Thank you for your listening. Any questions?
Let's thank our speaker. All right, so if you have any questions, please do come up to one of those microphones, state your name and affiliation, and then your question.
Takashi Sugawara from UEC. Thank you for the great talk. Can you show us the graph showing the performance?
Which graph?
Oh, yeah, this one is okay.
Yeah.
So say DSC, for example, does it mean the hardware you got the fingerprint from? That you know, this DAC or PWM or something like that. Is it the hardware fingerprint did you use for your proposal method?
Oh, do you mean that how we provide reliable authentication for the normal ones, or?
No, my point is, what is the fingerprint you actually used for your evaluation?
the question is like, do you think like voltage could be one fingerprint or something like this, or what? Well, that was a question, right?
Yeah.
So what are the characteristics being?
Yes. Yes.
The correctness of our fingerprints.
So the characteristics. So what exactly do you use to fingerprint the hardware?
Oh, okay,
Is
okay,
it
okay.
the voltage and so on?
Oh. The do you mean this? Yeah. We select many different hardware fingerprints related to previous work and go through the datasheets. And we select 4 or 5 of them. Should I explain it to you?
No. Yeah, that's fine.
Yeah, some.
And, how it's different from PUF, physically unclonable function?
What's the difference from half?
Yes.
Actually, you can deem our design as a special path because many paths actually need some special circuits. Yeah, but actually these hardware modules are in play, are deployed on the IoT devices already, so we don't need to design other special circuits, and we just explore them. Yeah, you can, actually, there are 2 types of paths to use. The first way is to reconstruct the secret key. We are different from this, and the second way is the path based on the challenge response. Yeah, we are similar to them, but more special because we don't need some special design. Yeah.
Thank you so much.
Then maybe one quick question from my side. You can fingerprint these devices because the manufacturing process is imperfect, right?
Yeah, right.
So would it even make sense to be more imperfect if I'm building a car key, such that I intentionally have some, let's say, well, incorrectnesses or these differences? So should we basically have more crappy devices that we use as car keys?
I'm a little confused.
Okay. So the question is basically, you like the measurements that you're doing, you can find differences because the manufacturing process is not perfect, right?
Yeah, right.
So, but basically, we don't want to have better manufacturing processes. We want to have worse.
Actually, if the manufacturer is perfect, the hardware will be almost the same. Then the hardware fingerprints will be useless. Not just our work. The whole hardware fingerprints will be useless. Yeah.
All right. Then let's hope for more imperfection, and let's thank our speaker again.